Hi everyone, and thanks for joining us today for our webinar, which is Eurocode7 ULS analysis made simple with LimitState GEO. I'm Tom Pritchard, and today I'm joined by our presenter, who is Dr. Colin Smith. He's the LimitState GEO product manager. The webinar today is going to last about 30 minutes, including a few minutes at the end for questions, which you can post in the Q&A functionality that you should hopefully have in front of you. For any questions that we don't manage to get around to today, then we will follow up via email in the next couple of days afterwards as well. We're also making a recording of this session available via our YouTube channel, details of which I will provide you with at the end. So without further delay, what I'm going to do is pass you over to our presenter for today, who is Dr. Colin Smith.
Okay, thank you, Tom. Welcome to this, our 7th webinar of 2022. Today, we'll be looking at the Eurocode approach to material factoring and how to conceptualize this in LimitState GEO. We're also going to take a brief look ahead at what could arise in the next version of Eurocode7 and how this relates to ultimate limit state numerical analysis. So to this end, I'll be using software directly to illustrate the points, but as this is a short presentation, the main aim is to give you a flavor of what the software can do. And there won't be time to get into details of the software functionality. However, there'll be a time at the end of questions. I'm also assuming some knowledge of Eurocode7. So we'll start with a brief background to technology in LimitState GEO. It's based on limit analysis, which is a rigorous method of analysis based on plasticity theory. I have to apologize, I picked up a cold recently. Hopefully things will be clear. So in limit analysis, the only assumptions are that soil behaves as an ideal plastic material, using, for example, a more Coulomb or Tresca yield surfaces familiar to geotechnical engineers. And examples of limit analysis include Coulomb wedge analysis, slip circle analysis, and Rankine analysis, if you can extend that field throughout the body. However, traditionally, limit analysis has been utilized only for simple mechanisms, such as 1, 2, or 3 Coulomb wedges, or Taylor slope stability slip circle analysis. However, this has changed with the development of the numerical method discontinuity layout optimization, or DLO for short. This is a systematic automated method of identifying the critical slipline pattern, published back in 2007 in the Proceedings of the Royal Society and a number of subsequent publications since then. And it poses a problem as a large but simple linear optimization problem. And it's quite straightforward to illustrate the steps. So we're taking a very simple example here, a rectangular block of soil for load on the surface and supports to the left and to the base. And unlike finite element method, what we do is we populate the domain with nodes. So here we've got 4 by 3, that's 12 nodes. And we connect every node to every other node with a potential slip line. So if we have 12 nodes, we've got 12 times 11 divided by 2, 66 possible slip lines. And then we use optimization to pick out of that large set of slip lines the critical collapse mechanism. And that turns out to involve just 6 slip lines, and we get this mechanism for this very simple problem. In the software, we're not using 12 nodes, we're typically using 500, 1,000, 2,000 nodes and millions upon millions of potential slip lines. So there's a very rich set of discontinuities to pick out the critical collapse mechanism. And it can be used to analyze a wide range of problems, including reinforced soil. It can be made to solve a problem using essentially emulating a 2-wedge analysis, as shown in this diagram. But typically, you're going to have many, many more wedges involved in the analysis, many, many more slip lines, and that enables the software to find more critical mechanisms. So, as I said, the software will automatically consider all failure modes that can be built using the discontinuities that connect any pair of nodes. And it therefore may find failure modes that are unexpected or don't fit with standard hand analysis idealizations. So, for example, gravity walls sometimes fail with combined sliding, bearing, and overturning behavior, as we can see in the diagram on the right, whereas classic hand analysis, you would analyze each one of those separately, but in combination, it's likely to be more critical. The software will identify this without any problem. And also sometimes with slope stability problems, particularly where the geometry or the profile of the slope has been imported from a DXF file, may find a local failure mode that's not identified by other methods, such as a method of slices. So here we've got an undulating surface, and what the software has done is pick out a local, very steep part of the slope and identified that there's a failure there, whereas other methods would tend to look at the global failure. Now, you may be interested in that local failure, or it may be just an anomaly. Probably means you've been over-conservative in estimating the slope soil strength parameters. So the easiest way to address that in the software is to isolate that local area as a separate soil body and just increase the strength slightly. Okay, so that's the background to how software works. Having done that, we'll first recap on ultimate limit state analysis, as this is important in understanding its relationship with the Eurocode approach to ultimate limit state. So in Eurocode7, you have to assess both ultimate limit state and serviceability limit state. The ultimate limit state is a hypothetical state that should never arise in practice. The aim of Eurocode7 is to ensure the probability of that ULS occurring is very low through the application of partial factors. And in order to undertake a ULS analysis, it's necessary to drive the system to collapse by some means. And this can be done implicitly or explicitly. In many conventional analyses and sort of calculations, the process is often implicit, but in a numerical analysis, you have to do it explicitly and demonstrate that you've driven the system to collapse. So there are number of different ways of doing this. Easiest one to follow is a load on a foundation. How much bigger do you have to increase that load to cause failure? And in software, we call that factor the adequacy factor. So whatever the load was to begin with, what do we have to multiply it by to actually get failure? So that could be an external load. We could also have a load arising from the self-weight of fill. So it is possible to ask the software how much heavier does the fill behind the wall in this case have to be to cause collapse. Or we can do it in terms of soil strength. How much smaller does the strength of soil need to be to cause collapse? Or by what factor F does the soil strength need to be reduced to cause collapse? And in this case, this factor is typically applied to all strengths simultaneously. So if you've got multiple layers of the problem, they will be factored down altogether. Okay, so we'll do a quick demo in the software just to show you how that all works. So this is a standard layout of the window. What I'm going to do here is simply run a built-in wizard. So the software can model any geometry problem you like, but it also has a built-in wizard to allow you to quickly build standard geotechnical problems. We're going to pick the gravity wall wizard here. I'm just going to accept all the defaults. So essentially, we've got a gravity wall here retaining a body of soil with a surcharge. And we're going to run this problem without any partial factors at the moment. So we need to understand where the adequacy is being applied here. And in the software, we have this tool called diagnostics, which is very useful, quickly summarizes what the setup of the problem. And we've got adequacy applied to one boundary load, which is B6. And if I click on that, it gets highlighted. So essentially, we're asking the software, how much bigger does that boundary load have to be to cause collapse? And if I click solve and I'm solving for factor load mode, then it will work that out and tell me that I need to increase that load by a factor of 20 to cause failure. Now that load was set to be 5 kPa. So it's quite unlikely you're going to get up to that kind of load to cause failure. So that's a factor of safety on the surface load. And if it's not a distributed load over the whole surface, but it's a specific isolated load, we can check that. So for example, I can isolate the middle of the middle load here. What I'm doing is clicking on a vertex button here, and I can drop a vertex to divide up this top boundary into 2 parts, and I'll add another one over here to divide it into 3 parts. And then I can click on individual parts and change their properties. So anything I click on in the software, its properties appear on the right in this property editor. And if I look at the loads here, these have been set as variable loads, and I'm going to set them to 0 in this case. And I'm also going to do the same for this particular case as well. So it's very quick and easy to edit the problem. So now I'm asking the software, how much bigger does this focus load have to be to cause collapse? That could be a much bigger load, potentially of smaller size. And it's given me a big number that's bigger, 36 times is the load, as you might expect. But I can look at these more focused areas. Now, as we said before, the fill behind the wall is also an unfavorable action. We can apply adequacy to this and solve. So if I click on the whole body, its properties appear on the right, and I can change its adequacy to true. So now the software is going to multiply this surface load and the backfill weight by a factor. And that's a number much smaller. That's just 3 in this case, because, of course, the backfill is what's generating most of the pressure on the wall. And if I look at the analysis here, I can click on a summary, and it tells me what the unit weight of the soil or the applied load was, what the design value is. That's a factored value, but we're using unit factors here. And then the collapse value, so that's a value it has to be to cause collapse, and these values need to be multiplied by 3.2. So we can do that. I should just point out that on this model, the collapse mechanism on the left intersects the boundary of the problem, so we really should extend that if that isn't a real boundary. And then finally, we could ask for a factor of strength analysis. So the software, again, will work out how much you have to reduce the strength by to cause collapse. And we'll get a slightly different failure mode. And again, if I click on this, it tells me all the strengths here and the fact that they've got to be reduced by a factor of 3. So we've really got to be very weak soil before we get collapse. So in summary, all these adequacy factors have different values, but are all greater than 1, which implies the system is safe, i.e. an unfavorable load has to be increased or the strength reduced to cause collapse. And for all types of application of adequacy factor, the only time you're guaranteed to get the same answer is when the adequacy factor equals 1, which means the system is on the point of the collapse, and you don't need to change anything for it to collapse. So just revert back to the PowerPoint. And just to summarize that, as I've said, if your adequacy factor is bigger than 1, your system is stable. If it's less than 1, you're unstable. And if you're applying to a load, you should apply it to any unfavorable load in the system. And that adequacy factor is going to correspond to a global factor of safety or an over-design factor if you've already applied partial factors. And generally, your optimal design will correspond to an adequacy factor equal to 1, where you've got partial factors applied. And therefore, it doesn't matter how you apply that adequacy factor. That just gives you a measure of over-design on particular parameters, whether it's strength or a load or a self-weight. So that will vary from problem to problem. And if you use a factor and strength mode, that's a little bit analogous to strength reduction and finite element analysis. However, LimitState GEO is what's called a direct method. It goes straight to the ultimate limit state using optimization and doesn't need to take incremental successive deformation analyses. Okay, so that summarizes how we get our models to the ultimate limit state. And we've got a range of methods available to us, which we can use to, check the sensitivity of particular loads or the sensitivity of the system to particular loads. Now we come on to Eurocode 7. Now, Eurocode 7, generally you would be applying factors before or after the mechanics calculation. So when you apply factors, you either apply factors, feed the factored parameters into your calculation model, and then do your assessment, or you run your calculation model with unfactored parameters, and then you factor the outputs, and then you assess your assess the design for compliance with the code. Now we're going to focus on the input factoring approach, the first one in this webinar. But just firstly to say that sometimes you can find examples in the literature where factoring is carried out inside the calculation model. This can be very challenging to do in numerical models, and there are various objections you can raise to doing this. So generally it's better to be factoring input or output before or after your calculation model. Calculation models, they include anything from conventional bearing capacity equations, finite element analysis, DLO analysis, method of slices, Rankine earth pressure theory, Coulomb wedge analysis, etc. They're all examples of calculation models. So as I said, we're going to focus on material factoring, which is an input factoring approach, which is design approach 1, combination 2. So that's the second column or third column here. So essentially, these are all applied as prefactors. So we apply a factor of 1.3 to variable actions. So they're generally known before the problem. You apply the calculation model, so they can be factored in advance, and the material properties are known before you run the model. So again, you can factor those in advance for input factoring. Then you have to show that you comply with Eurocode 7. So the core equation in Eurocode 7 is that you have to identify an action and resistance and show that a factored action is less than a factored resistance. For something like a foundation, that's quite straightforward. You have an action applied, load on the foundation, and the resistance is the resistance of the soil at failure. And in the software, you can find out that resistance because it's the action multiplied by the adequacy factor. So if your adequacy factor is bigger than 1, then your actions are automatically less than your resistances. Now, for more complex problems, such as slope stability, etc., or where you have multiple elements such as foundations, walls, slopes in the problem, it's not necessarily a clearly identifiable action resistance pair in the problem. However, if you can demonstrate the adequacy factor is bigger than 1, then this is equivalent to demonstrating that any action resistance pair in the problem, so you can choose them anywhere in the problem, satisfies the condition that factored actions are less than factored resistance. So that means that explicit verification of specific failure mechanisms may be omitted when using a numerical model that implicitly determines the most critical failure mechanism. So we'll just wrap up with another quick demonstration. So I'm going to run a variant of this gravity wall problem. So here we've got some layered granular materials in front, behind, below the wall. We have a surface load, and we can specify any of these loads to be favorable or unfavorable. However, for design approach 1, combination 2, all permanent actions are factored by 1. So we don't really need to worry about identifying them. They can all be left as essentially unfactored. So to run a Eurocode analysis with factors, the software has been set up so it can automatically apply factors. We use Analysis Scenario Manager here. And we can, from this drop-down box, pick factors or define our own. So I'm going to pick the predefined factors for DA12. They are applied on input. And then I can solve the problem. And I should have mentioned that we can also switch in the analysis between long and short-term analysis. So in the software, you are permitted to define both drained and undrained parameters for soils. That's typically going to be for your finer grained soils. And the software can be automatically switched from those two with just one click, which makes it very convenient for running those. Here, we're working with granular material, so it's always kind of drained analysis. So what we have in this problem, if I look at the diagnostics, is that we have adequacy applied to that surface load. So I will solve that, and we get a factor of 3.7. So that means the surface load has to be increased by 3.7 to cause collapse. So the design is clearly safe and complies with the code. And note we haven't explicitly considered an action of resistance. But as I said, any action resistance pair in the problem satisfies that equation. And actually, trying to identify specific action resistance pairs is a bit retrograde when using numerical analysis because it really fails to use the full power of the analysis. And what this analysis has done has shown that the design complies for DA12 for any failure mode, whether that's sliding, overturning, bearing, or any combination. There's no need to check those separately. Now, we could do the same thing using a factor strength mode here. And again, we're just looking for an adequacy factor that's bigger than 1, but it gives us a different information about the problem. It tells us what additional margin of safety we have over and above the factor of 1.25 that Eurocode applies to tan of phi dashed for these granular materials. So we're going to get a different factor to the one on the load, and here it's 1.367. And if I click on the answer there, you can see what it's doing. These were the values defined for the granular materials. These are the design values, which are the Eurocode factored values. And then over and above that, you have to reduce them further to these values by factoring by 1.36 to get collapse. So again, you do comply with the code. Okay, so that covers that. And then just to wrap up, so I'll say a little bit about the new Eurocode7. So it's just been out for consultation. A comment, the latest draft. It has 3 parts now: general rules, ground properties, and geotechnical structures. So there are chapters for a range of different structures, including reinforced, fill, and soil. There are additional clauses and guidance for users of the numerical models, improved guidance on water pressure factoring, and restructuring and enhanced clarity on the partial factoring. But the core values currently remain unchanged. And there are a lot of other changes. So, in summary, I hope what I've shown you is that Eurocode7 methodology and terminology is built into LimitState GEO. We can solve any ultimate limit state problem type. We don't have to make any idealizations or correction factors for non-standard geometries. There are no assumptions built in like interslice forces for method of slices. And there's no need to learn how to use many different programs. The same program can solve any ULS problem. It's interactive. I haven't been able to show you that much here, but hopefully you've seen it's quick. We can edit the problem quite quickly, and we can answer what-if type questions. In the scenario manager, we can run different analyses with simple global switches, such as switching the partial factor set or switching from long-term to short-term or drained, undrained analyses. In terms of factoring, material factoring, which is an input factoring approach, is the most straightforward. There's no need to verify specific failure mechanisms. The software will automatically identify the most critical failure mechanism. And a very brief summary of Eurocode 7 is that it has been expanded to address a wider range of issue and improve clarity for numerical modelers. So that takes me to the end of our webinar, and there's a few minutes left for questions. So if you have any questions, please post those. Okay, I have a question about water. So again, in the software, we can apply water. We can draw that using simplest way is to draw a water table. So I can use this water table tool and draw on a water table, for example, here. And then that analysis is an undertaken. So this is kind of a bit of flooding on this wall. And if we solve that, let's go for factor load, then we should get a reduced factor of safety because of the presence of the water. We get yes, we need a smaller increment on that load in order to cause failure on that particular wall. So modeling water is straightforward. Question about the loads. So if we click on the loads here, didn't have time to go into that, but the loads themselves have been split into 3 according to the Eurocode. So you can define separate permanent loads, separate accidental loads, and separate variable loads. And you can apply adequacy independently to each one of those. And you can specify whether those loads are favorable or unfavorable. Now, that is generally more relevant for design approach 1 combination 1, where these receive different factors. But for design approach 1 combination 2, certainly all permanent actions are factored by 1, so it doesn't really matter if they're favorable or unfavorable. But it does matter if you've got a variable load, then it's important to define that as unfavorable, so the software knows to apply the factor of 1.3 to that load in order to produce the analysis. So what we should have seen there is that the characteristic load we had applied was 10, the design value is 13, so that's factored up by 1.3, and then it has to be factored by another factor of 2.3 to get a collapse state. Okay, I think we've kind of run out of time there, so I'll pass back to Tom just to wrap up. So thank you very much for your attention, and I hope you found that useful.
Thanks, Colin, and thanks to everybody for attending today. I do hope you found the webinar informative, and as I mentioned at the start, if you have any questions as a follow-up to the webinar, then please do send them across to us at info@LimitState.com, and we'll be more than happy to answer them for you. We'll also be uploading a recording of this webinar to our YouTube channel in the next couple of days. So yeah, keep an eye out for that. We'll be sending out a link to it in the follow-up emails from the webinar registration. For more information on LimitState GEO, you can visit our website and also send us an email, and similarly follow us on LinkedIn and Twitter. So we've got our details there. And lastly, please look out for our other webinars that will be dealing with LimitState GEO coming into 2023. We'll be sending out event notifications both via email and also on our social media there. So lastly, again, thanks all for attending today, and hope you have a good festive period and you're able to join us for one of the future sessions. Goodbye.